And since the connection of the negative terminal is not shown over here, therefore we will connect the negative terminal to the ground. The same thing which I have mentioned right now is done over here. From node A, you have R1, then the positive terminal of the voltage source E2 is connected to R1 and the negative terminal of E2 is connected to the ground. So basically this network has been redrawn over here. Now, we have to indicate the voltages and current as shown in the original network. So, V1 is the voltage across R1 with the positive polarity of the voltage V1 is with E2 and the negative polarity is with node A. Thus, we mark V1 like this. Then there is another voltage which is marked, that is plus minus V2. V2 is the voltage across R4. So, as we can see that the positive potential is connected to A and the negative potential is connected to the ground. So, we have marked V2 like this. The positive potential or the higher potential is connected to A and the lower potential is connected to the ground. Current I is the current flowing from node A towards the voltage source E1. We have marked this current like this. We have marked three other currents which is shown over here, that is I1, I2 and I3. Because if we consider this to be a node, then according to KCL, I1 will branch out from this point. So if we consider this as I1 and this current as I prime, then at this point I prime will also divide into two parts, I2 and I3. Now, as you can see that in this particular circuit there are three complete loops. That is, this is one loop, this is another complete loop and this is the third loop. So, applying KVL, we can determine V2 over here. We are moving from the negative potential towards the positive potential. Therefore, this is plus V2. Again, we are moving from the negative potential towards the positive potential. So, this is plus E1. Plus V2 plus E1 equals to 0. Therefore, we determined that V2 is equals to minus 6 volts. Again, over here we have a complete loop. Hence, if we apply KVL over here, we can determine V1, which is basically 24 volts. Now, if you notice carefully, you'll see that this branch, this branch, this branch and this branch, all these four branches are parallelly connected. So, applying Kirchhoff's current law, we can determine I using the formula I equals I1 plus I2 plus I3. All these branches, that is R4, R3 plus R2 and R1 plus E2, that is the whole branch, will have a potential drop of 6 volt. Why? Because they are all connected in parallel configuration. Thus, using the voltages and the value of the resistances, we can easily determine the current flowing across these three branches. Hence, we can determine I using KCL. Example 3. Calculate the indicated currents and voltages as shown in this network. Now, the first step is to redraw this network. To simplify it, well, if we observe carefully, we'll see that on the left hand side, R1, R2 and R3 are connected in series because R1 has one common node with R2 and R2 has one common node with R3. Then this entire branch is in parallel with R4. After that, this entire configuration is in series with R5. And if we go on the right hand side, R8 and R9 are connected in series because they have one common node and no other element is connected at this point. Then this branch is in parallel with R7. Then this section of the network is in series with R6. E is the source and this side of the network is parallel with E, as well as the left hand side of the network is parallel with E. So, at first we find out the combined resistance of R1, R2 and R3, which in this case is 4 plus 8 plus 12, 24K. As I've mentioned before that this 24K is basically parallel with R4. And then this entire combination is in series with R5. And the total resistance on this branch is in parallel with the voltage source E. On the right hand side, we find the combined resistance of R8 and R9, which in this case is 6 plus 3, 9K. This combination of resistances is connected in parallel with R7. And this configuration is in series with R6. And this entire branch from this node till this node is connected in parallel with E. So the simplified network is this one. Then we marked the currents as shown over here. Since now we have the simplified network, thus we can easily determine the currents and voltages as shown over here. The next topic which we'll cover is source conversion. Over here we'll see how we can replace a current source with an equivalent voltage source and vice versa without affecting the network. Well, the symbol for an independent current source is this one, where the arrow indicates the direction of the current flowing. The current source is often described as the dual of the voltage source. Just as a battery provides a fixed voltage to a network, a current source establishes a fixed current in the branch where it is located. If you consider network A and network B, then both of them are the same network. The only difference is in the configuration of the source. In this case, there is a voltage source, and in this case, the voltage source is replaced by an equivalent current source. It is very important to remember that although there is a source conversion taking place, but the current flowing through the load must be the same. It must remain unchanged. If you observe carefully over here, there is a resistance Rs which is connected in series with the voltage source. This is basically the internal resistance of the voltage source and must always be connected in series with the voltage source. When we convert the voltage source to a current source, the series internal resistance Rs must now be connected in parallel with the current source and be represented as Rp. This conversion takes place using Ohm's law, that is, I equals